Okay, in this problem, we have air initially at a pressure of 1,400 kilopascals and a temperature of 500 degrees C is expanded through an adiabatic gas turbine. So the turbine is adiabatic, so this tells us that the heat Q dot is equal to 0. And it expanded to a pressure of 100 kilopascal and 127 degrees C. Air enters the turbine at an average velocity of 45 meters per second through the 0.18 meter squared opening and leaves through a 1 meter squared opening. So we have the velocity at the inlet and we have the area at the inlet and the area at the exit. Okay, note that we don't have the velocity at the exit. Determine the mass flow rate of air through the turbine and the power produced by this turbine. Okay, for us, this is problem number 5.17 on the problem pack. Let's sketch this problem. So what do we have here? We have a turbine. It's a gas turbine. We are using air just for simplification. What do we have? We have here the inlet, let's call it 1, and we have one exit, let's call it 2. What do we have at the inlet? We have the pressure. P1 is equal to 1.4 megapascal or 1,400 kilopascal. We have the temperature T1 is equal 500 degrees C. We have the velocity V1 is equal 45 meters per second, and we know the area A1 is equal to 0.18 meters squared. So this is our turbine. And at the exit, what do we know? We have the pressure P2. There is an expansion process, so the pressure will go down to 100 kilopascal. The temperature T2 will go down to 127 degrees C. And we have the area A2 is equal 1 meter squared. So the first thing we need to get is the mass flow rate. The second thing we need to get is the power out. W of the turbine, which is a power out, okay? This is a power out, so we anticipate that this term will be positive. Okay, so A, computation of the mass flow rate m dot. So we know by definition, okay, that m dot is equal to what? Is equal to velocity cross area over specific volume, okay? So m dot 1 is equal v1 a1 specific volume v1. Do we know the velocity v1? Yes, we do. Do we know the area a1? Yes, we do. Do we know specific volume? This one we don't. But we are using air, right? So we have air flow in here. So we can give it a try and apply the ideal gas law. So we have air, ideal gas. So therefore we can write that P1 V1 is equal to R T1. This is equivalent to say that our V1 is equal to R gas constant T1 over P1. We know the gas constant. We have T1 here, we have P1, so we have all the ingredients. So this gives us V1 is equal to what? Our gas constant is 0.287. Cross the temperature, this is our 500 plus 273 to convert it to Kelvin, and divided by the pressure here in kilopascals, this. And this will give us a specific volume. V1 is equal to 0.1585 cubic meters per kilograms. So this is done. We have V1 that we can replace now here, okay? So m dot is equal to what? Is equal to V1 A1 over specific volume 1. And this is equal to what? V1, our 45 meters per second, cross A1, the area 0.18 meters squared, over our 0.1585 cubic meters per kilograms. And this will give us a mass flow rate of 51.1 kilograms per second. The second question is asking us to calculate the power produced by the turbine. Okay, so B, computation. Of the power produced by the turbine. I'll write it just W dot T. So this is an open system, okay? So, and the first thing we need to do, which is a good habit, is to apply the conservation of mass, okay? So conservation of mass. So the conservation of mass is telling us that dm over dt, control volume, is equal to what? Is equal to the summation inlet, m dot inlet minus the summation over all the exits, m dot exit. We can consider steady state here by how many inlets? One inlet, one exit. So this will lead to 0 is equal m dot 1 minus m dot 2, or simply m dot 1 is equal m dot 2, and let's call it m dot to make our life easier. So this is good. Next step, first law of thermodynamics. We are looking for the power, so we'll be using the first law of thermodynamics. The first law of thermodynamics will give us that dE over dt, the change in energy in the control volume, is equal to what? Is equal Q dot control volume minus the power control volume, this is exactly what we are looking for, plus the summation over all the inlets, m dot inlet cross enthalpy inlet, plus 1 over 2 V inlet squared, plus potential energy inlet, minus, what do we have at the exits? M dot exit cross enthalpy exit, plus 1 over 2 V exit squared, plus the potential energy exiting. Let's make some assumptions here. So we assume steady state here, so we assume steady state here, so this is by. We are told this is a adiabatic turbine, so this one will disappear. This one will leave it. This is exactly what we are looking for. And what else? So we have the inlet velocity, okay? So therefore we won't neglect in this case the change in kinetic energy, okay? We could actually, but since we are given V1, we will just use it. But this one we don't have it, so we have to find a way to get it. And we can neglect the variation in potential energy. The objective of a turbine is not to increase your potential energy. So this will end up simplifying this and bringing this guy to the left. We'll get the power of the turbine is equal to what? Is equal to m dot 1 cross H1 plus 1 over 2 V1 squared minus m dot 2 cross H2 plus 1 over 2 V2 squared. But here we just put that thanks to the conservation of mass that m dot 1 is equal to m dot 2 is equal to m dot. So therefore, this will be the same, m dot and m dot, and we can rearrange them, enthalpies, and then variation in kinetic energy. Given us m dot cross h1 minus h2, so this term, plus m dot cross the variation in kinetic energy, v1 squared minus v2 squared over 2. Are we dealing with an ideal gas? Yes, we are. We have air. So therefore, this term, if we assume that Cp is also constant, we can write it as m dot cross Cp. This one will become Cp delta T, or T1 minus T2, plus m dot cross v1 squared minus v2 squared over 2. Okay, let's check what we have here. M dot, we just calculated, so this is done deal. Do we have T1? Yes, we do. This one is good. Do we have T2? Yes, we do. This is fine. M dot, we said we have it. Do we have V1? Yes, we do. Do we have V2? Oops, we don't have it. So we need to calculate V2. As soon as we get V2, we can plug all the values here, and we will get our power. Okay, so we reached this formulation, and we notice that we don't have V2. So to get V2, what do we have? We have the definition of the mass flow rate, m dot 2, which is equal to m dot 1, is equal to m dot, is equal to V2, what we are looking for, cross A2 over specific volume V2. Do we have the area? Yes, we do. It's 1 meter squared here. Okay. Do we have m dot? We calculated it's equal to m dot 2 is equal m dot 1 is equal m dot. So we have to get the specific volume in this case. So we can write that this is equivalent to say that our V2 is equal to what? Is equal to m dot 2 cross V2 over A2. And this one is equal to m dot 1 is equal to m dot. For V2, the specific volume V2, are we dealing with an ideal gas? Yes. So, but P2, V2 is equal to RT2. This is equivalent to say that our specific volume V2 is equal to R temperature T2 over P2. And this is equal to what? It's equal to our gas constant, 0.287, T2 127 plus 273, always in Kelvin, divided by P2, and this is 100 kilopascal. And V2 will be equal to what? Will be equal to 1.148 cubic meters per kilograms. Okay, you will see that basically it's higher than V1. Okay, there's an expansion process here. So now that we have this V2 here, we can plug it here. So then our velocity V2 in this case is equal to m dot cross m dot 2 V2 that we just calculated over A2. It's equal to what? Our mass flow rate was equal to 51.1 kilograms per second cross 1.148 over A2, 1 meters squared. And this will give us a velocity of 58.66 meters per second. Okay, almost there. Now we have this one, so this one will become checked. We have all the ingredients now, so we can calculate the power of the turbine is equal to what? Is equal to our mass flow rate. So 51.1 cross our Cp value 1.048 cross the difference in temperature in Kelvin 773, this is our 500 degrees C, minus 400. This is our 127. This is the first term. This is this one. Plus the mass flow rate again, 51.1. Cross the velocity V1, it's given, which is 45 meters per second squared, minus V2, which is 58.66 squared over 2, and be careful again, we divide by 1000 this term to have it in kilojoules per kilograms, otherwise it will be in joules per kilograms, and it won't match this one in terms of units. And this will give us finally a work or a power plus 19,939 kilowatts of work. So this turbine, under the following conditions, produces 19,939 kilowatts of work out.